Hi everyone, welcome back to this video series on Bitcoin. Separate execution of unlocking and locking scripts. In the original Bitcoin client, the unlocking and locking scripts were concatenated and executed in sequence for security reasons. This was changed in 2010 because of a vulnerability that allowed a malformed unlocking script to push data onto the stack and corrupt the locking script. In the current implementation, the scripts are executed separately with the stack transferred between the two executions as described next. First, the unlocking script is executed using the stack execution engine. If the unlocking script is executed without errors, e.g. it has no dangling operators left over, the main stack, not the alternate stack, is copied and the locking script is executed. If the result of the executing the locking script with the stack data copied from the unlocking script is true, the unlocking script has succeeded in resolving the conditions imposed by the locking script, and therefore the input is a valid authorization to spend the UTXO. If any result other than true remains after execution of the combined script, the input is valid because it has failed to satisfy the spending conditions placed on the UTXO. Pay to public key hash P2PKH. The vast majority of transactions processed on the Bitcoin network spend outputs locked with a pay to public key hash or P2PKH script. These outputs contain a locking script that locks the output to a public key hash, more commonly known as a Bitcoin address. An output locked by a P2PKH script can be unlocked spent by presenting a public key and a digital signature created by the corresponding private key. For example, let's look at Alice's payment to Bob's Cafe again. Alice made the payment of 0.015 Bitcoin to the cafe's Bitcoin address. The transaction output would have a locking script of the form of OP_DUP_OP hash 160 cafe public key hash OP equal verify OPCHEC. The cafe public key hash is equivalent to the Bitcoin address of the cafe without the base 58 check encoding. Most applications would show the public key hash in hexadecimal encoding and not the familiar Bitcoin address base 58 check format that begins with a 1. The preceding locking script can be satisfied with an unlocking script of the form cafe signature cafe public key. The two scripts together would form the following combined validation script: cafe signature cafe public key ODUP OP hash 16 cafe public key hash OP equal verify OP check sig. When executed, this combined script will evaluate to true if and only if the unlocking script matches the conditions set by the unlocking script. In other words, the result will be true if the unlocking script has a valid signature from the cafe's private key that corresponds to the public key hash set as an incumbent. Figures 6, 5, 6, 6 show in two parts a step-by-step execution of the combined script which will prove this is a valid transaction. So you can see here figure 6.5 evaluating the script for a P2P transaction part 1 of 2, and figure 6.6 evaluating a script for a P2P transaction part 2 of 2. Digital signatures, ECDSA. So far we have not delved into any detail about digital signatures. In this section we look at how digital signatures work and how they can present proof of ownership of a private key without revealing the private key. The digital signature algorithm used in Bitcoin is the elliptic curve digital signature algorithm, or ECDSA. ECDSA is the algorithm used for digital signatures based on elliptic curve private public key pairs as described in elliptic curve cryptography. ECDSA is used by the script functions OP check sig, OP check sig verify, OP check multisig, and OP check multisig verify. Anytime you see those in a locking script, the unlocking script must contain an ECDSA signature. A digital signature serves 3 purposes in Bitcoin. See the following sidebar. First, the signature proves that the owner of the private key, who is by implication the owner of the funds, has authorized the spending of those funds. Secondly, the proof of authorization is undeniable, non-repudiation. Thirdly, the signature proves that the transaction or specific parts of the transaction have not and cannot be modified by anyone after it has been changed. Note that each transaction input is signed independently. This is critical as neither the signatures nor the inputs have to belong to or be applied by the same owners. In fact, a specific transaction scheme called coin join uses this fact to create multi-party transactions for privacy. How digital signatures work. A digital signature is a mathematical scheme that consists of 2 parts. The first part is an algorithm for creating a signature using a private key, the signing key, from a message, the transaction. The second part is an algorithm that allows anyone to verify the signature, given also the message and a public key. Creating a digital signature. In Bitcoin's implementation of the ECDSA algorithm, the message being signed is the transaction, or more accurately, a hash of a specific subnet of the data in the transaction. The signing key is the user's private key. The result is the signature sig f hash MDA, where DA is the signing private key, M is the transaction of or parts of it, F hash is the hashing function, F sig is the signing algorithm, sig is the resulting signature. The function fsig produces a signature that is composed of 2 values commonly referred to as OR and SSIG or S. Now that the 2 values OR and S have been calculated, they are serialized into a byte stream Now that the 2 values OR and S have been calculated, they are serialized into a byte stream using an international standard encoding scheme called the Distinguished Encoding Rules, or DER. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing, and thank you.